I'm Lana.
And I'm Gigi, and we're both members of FTC Team 12827, the Crazy Cat Ladies.
Thank you for joining us today for another edition of the Safe Spring Saturday Seminar Series.
Wait a sec, what day is today?
June 27th.
Just as I thought. It's technically not spring anymore. The name of our video series is out of date.
No problem, I'll get that fixed. Welcome everyone to the Safe Summer Saturday Seminar Series.
Much better.
So Gigi, what do we have for everyone today?
I'm glad you asked, Lana. Today we're going to talk about another Java library called Nyan that the Crazy Cat Ladies have created to help teams take their control systems to the next level.
Another Java library?
Yes, a few Saturdays ago, we presented Schrodinger, a library that helps teams create state machines. If you haven't seen it, you can still find that video on our YouTube channel and learn about Erwin Schrödinger's frightened hypothetical cat.
Got it. Schrodinger for state machines. What does Nyan do and how did it get its name?
Nyan includes quite a few things, but probably the most important is the framework it provides for creating subsystems. In Nyan, subsystems can contain other subsystems, and so on and so on and so on. To reflect this potential endlessness, we named it after the famous Pop-Tart Rainbow Space Cat with the song that goes on forever. Nya is the Japanese word for meow, and the song you hear in the Nyan Cat video is called Nya 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 Nya.
I remember when we used to love the Nyan Cat song in FLL, and this, folks, is why we are called the Crazy Cat Ladies. So tell me more about subsystems, Gigi.
A subsystem is a self-contained system within a larger system. In FTC, complex control systems are best organized into multiple Java classes. Mapping these classes to parts of the robot that can make a conceptual unit is helpful.
So would that be like having a class named ARM that contains the code for controlling an ARM?
Exactly. If you look at the example op modes that come bundled in the FTC SDK, there is a hardware pushbot class that contains drive motors and servos for an ARM. Following the Nyan approach, these could be broken down into separate drivetrain and ARM subsystems, which is helpful as robot components begin to become very complex on their own. Nyan also provides a lot of features for subsystems, which we'll talk about.
Can you give another example of how subsystems can be used to break down a control system into smaller parts?
Sure. If you imagine a robot which collects and throws balls, it might have a set of subsystems like these. Robot is composed of a ball throwing system, which is composed of a ball collecting system, which is then composed of a motor and a color sensor. Also, a flywheel system is composed of a motor and a touch sensor, and a drivetrain system, which is composed of many different parts.
Thanks. That makes sense. So is there any connection between Schrodinger and Nyan?
Yes, in fact, Nyan builds on Schrodinger so that you can use state machines in your subsystems. This can be very useful to allow for multiple subsystems to perform a complex series of operations simultaneously. Nyan also uses a data logging system from Schrodinger that provides an easy way to get data, which can be used to troubleshoot the operation of your robot.
How can a team get started with Nyan?
Both Schrodinger and Nyan have code lab tutorials which take you through your first steps with each. You'll see in the Nyan code lab that you'll need to include the Schrodinger library in your project if you use Nyan, even if you don't create any state machines. In the code lab, you'll start with a fresh copy of the FTC SDK and Android Studio. You'll first create a very basic op mode to make sure that your setup, including Android Studio, driver station, robot controller, etc., is working properly.
Here, look, you can see a boring op mode.
Not for long, though. Next, we'll create another class called Robot, which has subsystem as its base class.
Okay, question though. If a subsystem is a system within a system, then what system is this robot class a part of? Almost got my tongue tied there.
That's a good point. The way the subsystem class works is an example of what is known as the composite pattern, where an object contains objects of the same type or class, and those objects can contain more objects of the same type, and so forth. So, when using Nyan, all of your subsystems will properly be called subsystems except the robot subsystem at the top. There it's a bit of a misnomer.
It looks like this robot must be a lumberjack. All it does is create logs.
Yes, we're taking baby steps. And the point here is to show how a subsystem only needs to override the methods where it has special functionality. Also, we see the data logger class from the Schrödinger library that we mentioned earlier.
Does the op mode have to change now that we've created this robot class?
Yes, in the op mode, we need to create an instance of the robot class and then invoke all the methods that correspond to the various events that happen while running the op mode.
Will we need to do the same thing for the subsystems that make up the robot?
No. As we'll see in a second, subsystems are connected to the subsystems they contain, and they automatically take care of calling these methods at the right time.
It sounds like subsystems are like folders in a computer file system. They can exist on their own, but can also contain other folders inside of them.
Exactly. And next, we're going to create a couple of subsystems inside of our main robot class.
Okay, how about one subsystem is a warp generator and the other is a tractor beam?
Maybe in the next video, but in this one, let's go with something a little more common to FTC robots, a drivetrain and an arm. Again, we keep it really simple and even just describe the main logic of the classes in comments.
So this loop method would get called repeatedly while the op mode is running?
Yes, that's right.
Does the robot class change when adding these two new subsystems?
Yes, inside the robot class, we add code to create instances of drivetrain and arm, and then we add those instances to the robot's list of subsystems. That's all we have to do to wire up the init, start, loop, log, and stop methods so that they will be invoked on the new subsystems automatically.
Hey Gigi.
Yes, Lana?
I heard you like state machines.
Yes, I do.
So let's put a state machine inside a subsystem inside a subsystem. Is that something we can do?
Yes. In fact, that is our next example. Here we show how the drivetrain subsystem could be made more complex by creating state machines for driving or spinning. We create helper methods which allow us to engage those state machines or stop what the robot is doing. Again, we have kept things simple in the state machines, but you can imagine how different states for ramp up, ramp down, etc. could be used.
In the examples we've looked at so far, we've created new classes that extend the subsystem class. Is that always true?
Many of the subsystems you create will be specific to your robot, but Nyan provides a handful of subsystem classes for commonly used actuators and sensors so that you can easily compose your own subsystems that include these.
There are already classes in the FTC SDK for these. What's the point of also having subsystems for them?
Well, the subsystems wrap those SDK classes and provide some additional functionality, like logging and caching, without any additional effort.
Cache me outside, how about that? What's caching?
Caching means that the class avoids unnecessarily redundantly writing or reading from the component when it would have no real useful effect. Complex control systems can often require a lot of work to keep them fast, and this helps avoid one area where things can slow down and make the robot less reactive.
That sounds great. Any other cool subsystem tricks?
Yes, actually. One thing that we commonly found a need for was to move a servo or motor to a certain position out of a set of options. The Nyan class's multi-position motor and multi-position servo make it easy to implement this. You can specify the speed of the movement for motors and servos, and for motors you can set a timeout.
Okay, enough about subsystems. Tell me about one more thing that Nyan provides.
Sure. As you can imagine, much of what caused us to create Nyan was the need to handle complexity for autonomous op modes. With state machines and subsystems, we noticed that our autonomous op modes started to look very similar, and we were able to make a generic framework for them. Here's an example.
Interesting. Can you break down what is happening here?
Gladly. By extending the abstract auto class, we can create an autonomous op mode with very little code. First, you'll notice a red-blue auto config object. Autoconfig is a concept that we use to allow for adjustments to be made in init before running the op mode. We provide the red-blue autoconfig out of the box in Nyan to allow you to set red or blue side of the field using the gamepad at match time.
I see. So you don't have to create separate op modes for red and blue. That's really convenient.
Right. Then in the constructor, you see that we're setting an instance of our robot class as the robot subsystem for the op mode. The next method shows the setup for the autoconfig interface, which uses telemetry and the driver station gamepads. And the following method gives our autoconfig an opportunity to read the configuration from a file as a starting point.
And the state machine method at the bottom?
That's probably the most important part of the class. In this example, Awesome Auto State Machine essentially contains the list of instructions that the robot should follow for this particular autonomous op mode.
And folks will definitely want to watch our other video on Schrödinger to hear more about how a complicated state machine like that can be made.
Yeah. Over the past couple of years, we noticed that some of the same needs kept appearing year after year as we were creating our control systems. We wanted to put those things into libraries to better organize our projects, but also make them available to other teams so they can benefit.
For sure, programming is hard, and some of the concepts required to make a good autonomous program are really challenging. It's awesome to see all 4 robots moving around during auto. If we can help teams be more successful with their control systems in auto or teleop, that would make us really happy.
Right. So, for any teams out there who want to put some cat power in their robots, let us know how we can help. We'd appreciate feedback on how we can clarify the code labs, improve the Java doc, or add new functionality to the libraries that would make them better for you. Okay, then, one other topic. What are your craziest guesses about Ultimate Goal?
Most of the Crazy Cat ladies play a sport, so we are very excited for this upcoming season. I noticed many basketballs and soccer balls, so I'm hoping for some sort of ball throwing. And you?
Well, we've never tackled launching before, so we're ready for a fun challenge. We also noticed some pull up bars, so we're anticipating some lifting. Well, folks, that's it for today. We will take off next week in observance of Independence Day, and then we'll return on July 11th. See you later.